Welcome everyone to the first popular science talk of the program. We are pleased to have Professor Nishant Chandgotia to deliver the talk. He is a faculty at IIFR Camp Bangalore. He works on ergodic theory and dynamical systems. Today, the title of his talk is Can You Complete the Puzzle? So let's welcome him for today's talk.
Okay, so Dootika, as soon as she saw the title, she said that, "Oh, you're here to challenge everyone," and there's a puzzle. Sorry. So that is indeed one puzzle already solved. See, you can solve puzzles, and this is going to be an invitation for you to try this. It's something which has definitely bothered me for a few years now, and hopefully it also bothers you a little bit after the talk. First of all, many thanks for inviting me to give this presentation. It was a lot of fun preparing it. Hopefully you also enjoy hearing about it. So this is the basic outline of the talk, and we'll start with some philosophy about mathematics and how we do mathematics, and then we'll get into the actual math part of the talk. I'll talk about tilings of the infinite plane, and then we'll see why that's hard. And then we'll talk about tilings of the finite plane, and then we'll also see why that's hard. And then we'll eventually boil down to the main question which interests me right now. Okay. So, there are all of us, especially, I practice this talk on my wife, who is not a mathematician for parts. And we all sort of come with this belief that every statement is either true or false, right? That it should be true. It's either raining outside or not raining outside. Now, the mathematician in you might say that, oh, define outside, and then we'll stop the conversation. But at least, you have a sense that every statement is either true or false. And if that is true, suppose we look at a statement which is either true or false, there must be a way of finding out what the answer is. Right? That's another thing that is it raining outside? Let's go outside and see. And you know whether it's raining outside. So there must be a way to find this out. And these are questions which were, people grappled with it in the earlier 20th century. And it was made precise by Hilbert and Ackermann. And I was, preparing for the talk, I was looking at the papers. It was truly wonderful to see how they were thinking about these philosophical questions. But, these naive thoughts of what is truth, what is a proof, what is an algorithm, all of it was completely, okay. I will say, I was going to say destroyed, but maybe I will not say destroyed. I'll say it was enriched by the ideas from Gödel, Church, and Turing that showed that, at least the naive ideas are incorrect. And, things need not just be true and false, they depend on what kind of axioms you start with. And even if you know that something is either true or false, it's not necessary that you can find a method to find out what the truth is. But now suppose, let's go to a third question, which is also very interesting. Suppose you have a method of finding the truth. Okay, there's this procedure, and if you carry it out, then you will be able to find out what the truth is. Well, will it finish in our lifetime, right? I am making an inquiry. It's because I want to find out the answer. Now, if this method takes too long, then this method is not very useful. So it's as well as there being no method at all, right? So these are fundamental questions which has bothered, mathematicians, computer scientists, philosophers for a very, very long time. And I'm not going to, try to say that, oh, I will try to address these questions in some way or the other. I'm going to look at a very simple example. And I'm going to try to study that example. And so let's jump into it. So let's talk about tilings of the infinite plane. So suppose we are given square tiles with colors on the edges. Does anyone know who these two people are? Anyone? The person on the left, at least. Okay, so the person on the left is Roger Penrose. And hopefully the name is familiar to all of you, if not the face. And the person on the right is Daniel Shechtman, who is a chemist who you will become familiar with in a couple of slides. Okay. So you have these tiles, and these tiles are just plain simple squares. They're colors on the edges. And for each of these tile types, you have infinitely many tiles. So there are infinitely many Roger Penroses, and there are infinitely many Shechtmans. And now the rule of the game is that I can put two of these tiles together if the colors match. This is just like your jigsaw puzzle. I would have liked to draw a jigsaw piece over here, but it would have my creative skills, my artistic skills are not the best, so I just put the colors there. Okay, so this is like the jigsaw puzzle that you saw. You try to make pictures, you may try to make castles using these jigsaw pieces, and the rules are very similar to this. You were given some tiles, you're given some matching rules, and you try to put them together. And the question that we ask is, can we cover the entire plane with these tiles? In some cases, we can. So if we take the Shechtman tile and the Penrose tile together, then clearly there's a nice matching which takes place. Of course, I designed it that way. The yellow here matches with the yellow there, the blue matches with the blue, the greens match up, and the reds match up. So when you put them together, you get a nice periodic pattern on the entire plane. But now if I just took Roger Penrose alone, then I wouldn't be able to tile the plane with it. Because what would I place on the right of this? The green doesn't match up with the red. So now I'm stuck with one tile, my game is over. So there was a very famous logician in the 1960s, 70s, and so on. I would say philosopher, logician, so on, who wanted to know to what extent can computers prove theorems. And he asked this question, which was relevant to his research. Is there an algorithm which takes as input a set of tiles, and as output determines whether the plane can be tiled or not? Okay. So let's be very, very careful with the formulation of the question. The question is not asking whether, for a given set of tiles, I can find an algorithm. That's not what it's asking. In terms of computer science, theoretical computer science, for a single example, there always exists an algorithm. There's an algorithm which says yes, there's an algorithm which says no. So one of them has to be correct. What it's asking is that it will take all the tiles, this set of tiles that I'm interested in, it will take it as input, and this will go into this black box. And out of the black box will come the answer yes or no, which corresponds to whether the tiling exists or not. Okay. And so for the two examples, we saw how to construct ways of doing it. His PhD student, Robert Berger, disproved it in a very beautiful paper. He showed that there exists no algorithm which will take as input a set of tiles, and as output will tell us whether the tiling exists or not. Now, it's very important to notice a very fundamental fact, that if I know beforehand that there exists a periodic tiling, then I would be able to formulate an algorithm. I would just keep on going. And at some point, I would either hit a periodic pattern, much like the Penrose and Shechtman pattern, or I would not be able to extend any further, like the one with just Roger Penrose. So Robert Burger's construction, which showed that there's no algorithm for deciding, also showed that there are a set of tiles which can only tile aperiodically and there's no periodic tiling possible with them. This was further refined and popularized by Robinson in 1971, Raphael Robinson. And when you color coded appropriately, beautiful patterns appear. This is a hierarchical structure where you have small shapes appearing in bigger shapes, appearing in still bigger shapes, and there's repetition much like a fractal, which you learn about through this summer school. So you have this sort of self-repetitive structure. Yes. So one tile would be a square here. Now, there are a lot of colors associated with the edges, but I'm sort of hiding the colors and just sort of, color coding them according to, So I'm hiding a lot of details in this picture because, each tile should have colors and so on and so forth, but I'm ignoring that for the time being. I'm just bringing about a simplistic picture. So there are tiles also in the middle boxes. There are some signals which are traveling here and there, which, I'm completely ignoring. So it's a very beautiful paper by Raphael Robinson. I invite you to have a look at that paper. It's something that you can just sit down and read. If you know about Turing machines, it will become easier. If you don't know about Turing machines, you will learn. Okay. So in 1974, with completely different motivations, Roger Penrose came upon a set of tiles. So he was not looking at tiles like the way we are looking at. There are still, these shapes and there are rules on how they're attached, but they're no longer squares. And this gave rise to special aperiodic tilings of the plane. And you notice that it's very symmetric. When you look at it, it gives you a notion of symmetry. But it's not the notion of symmetry that you see like, it's not like if you translate a part of this tiling, you place it again, you see the same tiling again. It's more rotational symmetry. And now you notice that there are these stars. And this means that there's some rotational symmetry along the stars. Okay? So, I'm not giving you precise statements because that would take too long. Hopefully, if you have questions, do ask. And he writes in his paper, of course, he was motivated by physics. If you know Penrose, he was motivated by physics. But he wrote in his paper that, however, recently I wanted to design something interesting for someone in the hospital to look at. He had a friend who was in the hospital and he wanted to design something beautiful and he made this and gave it to his friend. Probably helped him pass his time a little bit. So, people took it up and now everybody wanted to make an aperiodic tile. And you will see that, like I'll show you why this has become a very popular question. In 1981, these physicists predicted that a crystal with such a structure must exist. And this prediction was quite revolutionary in its time because it went against something very, very fundamental in physics, going back to the likes of Aristotle, Plato, and so on. So the crystallographic restriction theorem said that if you have an orderly arrangement of atoms or molecules, then they can only have 3, 4, or 6-fold rotational symmetry. However, Daniel Sheckman discovered such a material. So this is a diffraction pattern of the material that he discovered. And as you can see, this is also rotationally symmetric. If you look at the central object, there's some rotational symmetry around it. There's a diffraction pattern. It sort of says that if you have such a diffraction pattern, then the material, the arrangement of molecules in the material must also have that kind of symmetry, which is rotational symmetry, 10-fold symmetry. And this broke the misconception that orderly arrangement of atoms must necessarily be periodic, and brought a big revolution to the field of crystallography and material science. So it was, I'll sort of describe how revolutionary it was in a second, but you probably have heard of the story of the person who proved that square root 2 is irrational. He was drowned in a well because people didn't like the fact that how can you, rationals are beautiful, how can you say that square root 2 is. So a similar, okay, not as extreme incident takes place with him. Linus Pauling, a two-time Nobel Prize winner, said that there are no quasi-crystals, just quasi-scientists. And the story goes like this, that the poor guy loses his job and eventually goes on to win a Nobel Prize himself. So this is an actual material showing a Roger Penrose tiling type structure. And, a few years before all of this, Kepler had a very similar picture. This is from his treatise. And then you can find similar structures in, in Byzantine or Islamic architecture, where you see similar patterns appear. And this is 1400s. Probably there were ones before this. And even to this date, so this is from 2023, where a single tile was found. Again, this is not formed of squares. A single tile was formed that if you put them together, then you get only a periodic tilings and not periodic ones. This one. So if I remember correctly, Smith among these people. So this was a question which was very well known, that whether there is a tiling which tiles only a periodic, a monotile as they call it. And this was open for quite some time. And Smith was an amateur mathematician who was just dabbling with various things. I don't exactly know how he came about it. He came up with a construction. He sent it to Mayers, Kaplan, and Goodman Strauss, who are mathematicians, and then they together sat down and proved that indeed he is correct. No, in this case, I don't think it was a real world object that got them to come up with this construction. By the way, can everyone hear the question? Otherwise, I'll repeat it. Okay, so just let me know if you want the question repeated. Great. So the center of the figure, this is, can anyone guess who this is? That's Linus Pauling. All right. So the problem that I spoke about till now, and I spent some time discussing it, it's a complicated problem and it deals with infinities. And whenever you talk about something with infinities, the solution to the Diophantine problem, so on, there's some possibility of undecidability. Now I'm going to simplify my life and I'm going to ask finite questions about finite objects instead of infinite objects. And hopefully we can answer them a little better. So we are going to change gears. We are going to not talk about a periodic tiling so on. Our tiles will be boring, uncolored ones. There will be no colors on the edges. They'll be, in fact, plain simple boxes with integer side nets. That's all I'm going to care about from here on. And we'll not try to tile the infinite space. If I just have boxes, it's very obvious how to tile the space, right? And they're uncolored, so I don't even need to worry about what comes next to what. So they'll be just placed next to each other, and they'll just be, and so tiling the infinite space is easy. But now if I give you a finite region and I ask you whether that can be tiled, that's a much more difficult question. So now that I have changed the kind of tiles that I'm dealing with, my questions change quite a bit as well. So it's like a traditional jigsaw puzzle, more like a traditional jigsaw puzzle. But now there's a procedure for finding the answer. You have this region given to you, you have a bunch of boxes, just try to place them in all possible ways. At some point, you'll figure out that there's no way to do it, or you'll find a way to do it, right? If I gave you a Sudoku puzzle and I gave you infinite time, you know that you'll be able to solve the Sudoku puzzle, right? So, but this might take a very, very long time. So let's get a feeling for these kind of questions. So here's a 6x6 grid, and I've removed the corners from them. So there are these two tiles, and the question I'm asking is very simple. Can you create this design on the left using the two tiles? For someone who has never seen this before, this is a very popular question, so I'm sure that you have seen this before. Can someone who has never seen this before take a minute to think about it, and like if you have an idea how to approach this? Yes. Yes. As many pieces as you want. Any volunteers? I saw a finger up, but I guess that was just, yes. So I'm not allowed to put things diagonally. So I'm not allowed to rotate these things. So I'll put the green one in the first corner, very good. Right side corner, okay. You mean like this? Right, right. So I wish I had more time. I have actual physical tiles in my office, and I would have liked you to try it out. And what would happen as you try it out, you would see that whatever way you would, so what would you do? You would fit in things in the corner, in this edge, and then you would try to put other tiles fitting next to it, right? Well, you place a tile over here, you place a tile over here, that forces a tile over here. And now you'll slowly start getting stuck. Okay? So the answer is no. And these blocks are dominoes. Let's make some easy observations. Each domino has size 2. Thus, anything that can be tiled by dominoes must have even size. Well, in this case, the size is 34, so that doesn't create any problems. So if I just removed one corner, then the answer is obvious, because you cannot tile something of size 35 with things of size 2. So maybe there's a tiling of this. But now let's color code this in a way. So I'm going to color these black and pink, and each domino covers 2 adjacent boxes. So in particular, anything which is under a particular domino, one of them will be black and the other will be pink. For people who are familiar with graph theory, this is a bipartite graph. So notice that there are 2 pink boxes missing. So the number of blacks is different from the number of pinks. So in particular, you cannot tile the area by dominoes. Okay. Let's try a harder puzzle. So now even people who are familiar with this, do you think this region can be tiled by dominoes? Take a minute, see if you can find a sorry? No. I think it got cut off. I'm so sorry. That's a domino. That's a 2 by 1, 1 by 2 and 2 by 1 tile. Sorry about that. I noticed this half tile and I sort of, no worries. I should have just drawn it again. Sorry about that. Any volunteers? Sorry. Oh, yes. It cannot be tiled. That is correct. In the top, this has to be a vertical tile. Perfect. Absolutely. Right. It will get cornered. Does everyone see the argument? It's a very beautiful argument, in my opinion. And indeed, this cannot be tiled. And I give you blocks, you would realize this immediately. Now, it has equal number of black and pinks. So there's a chance there might be a tiling. But now we notice that each domino pair pairs a black with a pink. So if there is a tiling and I gave you some black boxes, there should be at least that many pink boxes next to them. And vice versa. If there was a tiling in the background and I saw some pink boxes, then there should be at least that many black boxes next to it. So how many neighbors do these pink ones have? Well, I'm just going to give you the answer in interest of time. There are 11 of them. So that's fine. But like the example that she gave, if you look at those 5 black ones, how many neighbors do they have? Well, only 4 of them. So now if there was indeed a pairing, then you would get stuck over here, right? These 5 cannot be paired with these 4. There's one pink missing. So this region cannot be tiled. Of course, her proof was much more visual and much more elegant, but it was actually sort of hinging on this kind of an observation. Does everyone understand this example? This is kind of central to whatever we'll do. Okay, so let us look at the puzzle in a different way. Each domino matches a pink with a black, and we want to match the pinks and blacks. That's all we want to do. Okay, now instead of trying to tile the plane with these boxes, all I want to do is find a matching of the pinks and blacks. At the same time, you only want to be matched if you're next to each other. So a necessary condition is that for any set of pinks, you must have at least that many blacks, and vice versa. And in fact, there's a theorem. This is a very famous theorem due to Hall. So Hall's matching theorem says that there's a matching between the pinks and blacks if and only if this necessary condition is met. What is the necessary condition? If I take any subset of blacks, there should be that many pinks next to it. And if I take any subset of pinks, there should be that many blacks next to it. Okay? Let us see how this works, okay, in an example. So this is a very simple example. It's a box. And if I ask you to tile it with dominoes, you would do it immediately. You would just place everything horizontally. But let's suppose, let's forget that this is an easy example. Let's try to make it more complicated. And the reason to make it more complicated is that it will give you a way of dealing with this example a little better, dealing with general examples a little better. So what we are going to do is we'll try to match them randomly. The person who came up with this algorithm, the paper in which it was published, it was how to marry randomly or something like this. So you try to match these pinks and blacks randomly. Now, when you do it randomly, you'll be left with some tiles which are unmatched, right? Because you're doing it randomly, you'll miss some of them. So here in this example, I'm missing this pink and this black. So now I somehow want to match them. So what I'll do is I'll take the pink and then I'll select one of the blacks next to it and I'll match it with this. But now I'm in trouble because this pink remains unmatched. So then I'll match that. And then this remain unmatched. I keep on doing it. At some point, I'll reach the black also, which was unmatched. Now, to prove that this actually works, you will need the conditions which I gave you. Okay, so I'm not going to go through the details of the proof. Hopefully, it gives you a feeling and you can go back home and try to prove it yourself. It's a very nice exercise. So that's very good. Now we have found a way to solve a particular puzzle. But the natural question now arises is now suppose I give you a large example. How would you proceed solving it? You would list all the subsets of reds, all the subsets of blacks, and then look at how many neighbors do they have. What is the cardinality of the power set? The cardinality of the power set is 2 to the power the cardinality of the set, right? So if we started with a 10 by 10 example, it would take a very, very long time. So it would be 2 to the power 10 to the 10 times 2 to the power 100, or 2 to the power 100. Even if you take a millisecond to check each example, you take a very, very long time, probably longer than our own lifetime. So this is an algorithm. It works, but it is very, very inefficient. Do we all agree that this looks inefficient? So this can be solved efficiently in multiple ways. The problem which I showed you right now, the one earlier. In general, this problem is what is called NP-complete. So if you were to find a general, instead of the subset of Z square or R square, if you had instead a bipartite graph and you found a efficient way of solving this problem, you would win $1 million, I think. What was the millennium prize money? I forget. Probably $1 million. I don't remember. The money is not the main point. So the general problem is very difficult to solve, and we are not going to make any efforts trying to solve it. But this particular problem about the plane, and I take a subset of it, has a very, very beautiful and elegant solution. I'm going to highlight a solution given by Conway, Lagarius, and Thurston. So this takes us towards group theory, and if you actually understand what's going on in the background, then goes to geometric properties of groups, which we don't have much time for. So here are Conway, Lagarius, and Thurston. Right. So Conway, Lagarius, and Thurston were interested in solving this the following question. I'll give you a region, and I'll give you a set of tiles. When can you tile the region using the tiles? Okay. So what we are going to do is we are going to take each individual tile, and with the tiles, I'm going to assign some words. So for instance, when I go up, I will say U. And when I go across from left to right, I will say A. And of course, if I change my direction, I say A inverse or U inverse. Okay. So what would be the word which would come about here? It would be U, A inverse, then again U, A inverse, U to the power minus 2, A square. Okay. And that's what you see written over here. And you read it from in the, right to left instead of the way you're used to reading it left to right. So with all these tiles, I've associated a word. Okay, and this word has alphabet A inverse, U inverse, A, and U. Okay. So each tile is giving me a word. So let's name the tile T. The tile T gives rise to a word W sub T. And if a region can be tiled by these tiles, then what I want to say is that I sort of want to treat this W sub T as identity in the group. Formally, the way one would do it is by defining what is a finitely presented group, where the generators would be A and U. And these words that I found associated with these tiles would be the relations. Now, I don't assume all of you are well versed in finitely generated groups or finitely presented groups, but the idea is very simple. We all know some group theory. You have A and U. If A and U commuted with each other, and that was the only relation, what group do you get? Someone? Sorry? I heard a voice. Ah, I see. All right. So I'll give you the answer. If A and U had the only relation was that going from A to U is the same as going from U to A, that would give you an abelian group. That would give you a Z square. Okay? Because you could, the way you should think about it, and that's the way I think about it, is that you can move along in the direction A, you can move along in the direction U, and going from A to U is the same, going A and then U is the same as going U and then A. So instead of thinking of these things as abstract objects, you should think about them as walks. And you think about these as walks, and I'm saying that when you make this walk, you come back to where you started, and that's your relation. Now, if you're walking along and you say that going from A to U is the same, A and then U, horizontal and then vertical, is the same as going first vertical and then horizontal, what are you forming? You're forming a grid. And this grid is like Z square, tuples I and J, with the usual addition and so on. So it turns out that if you have these relations, then you can you get a necessary condition. So this here, you can perhaps identify that it can be tiled by these vertical tiles. This we all agree with, right? You just place these three vertically. So this region R gets tiled by T1. Well, let's take this corner as a starting point, as usual, okay? So what is the word associated to R? It's U cube, A to the power minus 3, U to the power minus 3, A cube, right? But now I can write it in the following way. I first traverse the rightmost tile T1. And that gives me U cube A inverse U to the power minus 3A. And then I look at the middle tile. And the middle tile will give me another word because I will just go here and then I will look at what letters appear as I walk around it. And then I'll get the last tile. Now, what have I told you? I have told you that these are like coming back to identity. Now, if each of these is like coming back to identity, then this whole thing is like coming back to identity. For people who have not seen group theory, this might be a little too much to digest, but hopefully you got some feeling for it. Okay. So for a m cross 1 and 1 cross n tile, the associated words are a to the power m u, a to the minus m u, and similarly that one, right? This is what we would have, right? So if I have something like this, I start at this corner and I go up, then I first see a u, then I will go across in this direction and I would see a to the power, I don't know, 1, 2, 3, 4, 5, a to the power minus 5. So that would give me an a to the power minus 5. And then I would go down and that would give me u inverse. And then it would give me a to the power 5, right? This would be the word which would arise for this tile. And similarly for vertical tiles. And now what I want you to think about is that this is a very complicated object. Instead, it turns out that this is equivalent in some sense, which I don't want to go into. I want to call this as coming back to where I started from, my identity. Instead of saying that this is identity, I'm going to just say that this is identity. And if I say that this is identity, then automatically I took you, I made identity, I came back to myself, and then I did a U inverse, so I'm back to identity, and then I made this movement as well, and this is also identity. So it turns out it's equivalent in some way, which I don't want to get into, to instead think of a to the power m as identity and u to the power n as identity. And using this, one can actually find a necessary and sufficient condition of tiling nice regions. So this uses a mix of analysis and algebra. So what I've described to you is an algebraic condition. And there's a corresponding analytical condition, which is about extension of Lipschitz functions. You put them together, you get a necessary and sufficient condition for tilings by m cross 1 and 1 cross n tiles. And this algorithm takes, not as long as eternity. It can be, it's actually quite efficient, as efficient as it can get, in fact. So there is some feeling for what was done in the past. Okay, so now we'll try to go towards the future about what are the questions I really want to solve in the next 7 minutes. Any questions? Yes. 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 Wonderful question. So I always, when I have to start, I come back to where the beginning. So suppose I wanted to start from here, I would go up, left, down, right. I covered first tile. Now I'm back to the starting point. So I start where I left. So now I'll go, I think this is for covering this tile. I would go here, then go up, left, down, right. And now I've come back to the starting point of this tile. And for this combination, right. Yes, exactly. So I would do an A inverse. Just give me a second. You would do an A inverse. And then you would have a U cube, A inverse, U to the power minus 3. and then A. That is correct, but you can sort of imagine that if you have an A and an A inverse, they cancel. So even though I have traversed it twice, I'm sort of traversing the entire rectangle step by step, each one tile at a time. Right. So you think of it as a conservative vector field. If you integrate, work done. If you go from here to home and back is 0. That's how you think of it. I can actually make that precise, but maybe we don't have time for that. Yes, 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 yes. And yes, that's a very nice way of thinking about it. And when you put a lasso, then you're actually conjugating the tile word around that. Okay, but we will. Other questions? That was very fast, I have to admit, but yes, go ahead. This one. Yes. So I always get confused which direction is M and which direction is N. So I'm sorry. Yeah, yeah. So please make the necessary permutation, and it's correct. Okay. Other questions? Yes. Yeah. That is a very nice question, but yeah, I will. Yeah, it can be done exactly by this method, and yeah, I won't be able to get into that one. It's a favorite question that I have, but yeah, I will have to. Right. So the question is, if you have a rectangle, and correct me if I'm wrong, and you know that all the side lengths of the tiling rectangles inside, one of the sides is always integer. Then you can prove, it's a wonderful exercise, that for the bigger rectangle, at least one of the side lengths is an integer. And the proof technique is very, very close to this. You can take that as a puzzle, another puzzle, but this one is solved. Let's go to one which is unsolved. Okay. So the main problem I want to address is what is called the cylinder problem. So we are going to be interested in what are called trimers. So far I was discussing dimers or dominoes. An interesting object close to it is what are called trimers, which are 1x3 and 3x1 tiles. Okay, so the question is very simple. You have some pattern at the bottom, you have some pattern at the top, and everything else is just flat. Because there's a 1/3 and 3/1, I'm going to allow for distance 3n between them. And now this is my puzzle. N can be as large as I want. Can I tile this figure? So till now, what my puzzle was that I was given this board, and this is where I would place the puzzle pieces. Now what I do is I'll allow for the board to be elongated. And now I ask the same question, can I somehow tile this region, which is possibly as large as I want, by these tiles? And notice what we discussed earlier, you had A cube is identity and U cube is identity. Okay? So what does the top boundary give? I'm going to do this very roughly. So if I mess things about, then don't complain. So I'm just going to read from left to right. What the top boundary would give is an A, U inverse, A, U, A, and so on. And you take your A cube and you remove it, U cube and you remove it, you get this. The bottom boundary is going to give you a similar word, where you just go along and you write down what the word is. Now, these two words are not the same. But what did Cornwell, Lagarius, and Thurston tell me? They told me that if this region was tileable by 3 by 1 and 1 by 3, then going around, I should come back to identity with this relation that whenever I see an A cube, I just forget about it. When I see a U cube, I just forget about it. So this boundary word is like a fingerprint of the region. And I am out of time, but can I take 5 minutes more? So this boundary word is like a fingerprint of this region. If the region is tileable, then the top and the bottom must agree. Right? That's the necessary condition which Cornwell, Lagarius, and Thurston gave me. And with some work, a little non-trivial work, you can prove that it's also sufficient for this problem. If the two words are the same, then you can find a tiling. So this is giving you a very, very easy procedure for solving this puzzle. Look at the bottom line, look at the top line, look at the words which arise, see if they are the same. If they are the same, you're done. So for people who are familiar with Markov chains, and which you're going to learn about very soon, I guess, we are trying to find out irreducible components of the Markov chain. This is what the problem actually is. For people who are familiar with limit shapes, we are trying to look at random tilings and trying to find patterns within them. So I'm trying to look at uniformly random tilings and trying to understand what kind of limit shapes appear. I don't want to go into too many details, but these questions which I'm asking are simple and combinatorial, but arise from, they have motivation coming from probability and from statistical physics. So this problem that I described gives you a necessary and sufficient condition. And the question that we have in my mind is whether there's a similar procedure in higher dimensions. So now what we'll do is, instead of having, like, all this while I have been dealing with two-dimensional objects and trying to tile them. But what if I try to do three-dimensional objects instead? So I had a cylinder, horizontal cylinder like this. Now I have a cylinder like this. And instead of trying to tile by 1 by 3 and 3 by 1, I will try to tile them by 1 by 1 by 3, 1 by 3 by 1, 1 by 1 by 3 by 1 by 1. These three tiles. So I have the same shape. I have some pattern at the bottom, some pattern at the top, and I have horizontal sort of flat edges. It's like a castle with a bottom castle as well. I don't know how to think. A castle with a reflection, if you want to say. Think of it. And here's a way to think about this. You slice the bottom, and that slice will give you some zeros and twos and ones, right? Whether you have a gap of 1 or a gap of 2 or a gap of 0. And similarly, you'll get a slice at the top. And now we want to know whether we can go from A to B. And what are the steps? I am only allowed to place 1 by 3, 3 by 1, 1 by 3 tiles. So if I see 3 consecutive tiles at the empty spaces or things at the same height, I add 1 to them. So I added 1 on this corner. Okay. Another move, that's like placing a trimer or a 1 by 3 by 1 shape. Now, if I see any site which has height less than 3, I can add 3 to it. This is also something which is allowed. And we continue till all the heights are greater than 3, and then we go modulo 3, and we start again. And this is like placing these different patterns where you start at the bottom of the castle and try to start building it up. You don't care what the height of the castle is. You just want to know whether the top pattern can appear sometime or not. Okay. Oh. So in 2 dimensions, these boundary words gave very effective ways to test this. In 3 dimensions, even for simple boxes like these, we have no idea how to approach this question. And here's your puzzle for the day. What is the 3-dimensional analog? Don't look at me for answers. I don't have them. And nobody does. So thanks for listening. Sorry for overshooting my time.
This wonderful talk. If you have any questions, please feel free to ask.
Yes, of course. So, okay, one thing can be done. The 2-dimensional idea, you could sort of look at, you have this, I wish I had bought my tiles. So you have this bottom castle area, and you can look at it column by column, and then you can look at these slices. They won't give you the full answer. But yes, that's a very good place to start. Actually, I don't know if it will give the full answer. I have tried investigating that. I don't think it does, but yes, it's something which should be investigated.
So let's thank the speaker once again.
Yes.